Spiders use adhesive, stretchable, and translucent webs to capture their prey. However, sustaining the capturing capability of these webs can be challenging since the webs inevitably invite contamination, thus reducing its adhesion force. To overcome these challenges, spiders have developed strategies of utilizing webs to minimize and eliminate such contamination. Spiders build minimal webs and then wait for prey to come in contact with these webs. After sensing vibrations of the web caused by the contact, spiders wrap the weakly caught prey with additional thread to supplement the adhesion force of the existing web. Thus, their sensing strategy helps to minimize contamination by allowing the spiders to build minimal webs. Furthermore, to recover the capturing capability of contaminated webs, spiders pull and rapidly release their webs in a manner similar to a slingshot, causing the contaminants on webs to bounce off by inertia force. In this regard, spiders can sense and clean using their webs alone, and these functions act synergistically to capture prey. Inspired by how spiders capture their prey, we emulate the abilities to capture, sense, and clean using spiderwebs in our ionic spiderwebs. All of these features were realized with a single pair of threads consisting of ionically conductive organogel encapsulated by a surface-treated silicone rubber. Through electrostatic adhesion, the ionic spiderwebs developed in this study robustly captured various types of targets, including an aluminum with a 68-fold greater mass. The electrostatic induction sensing allowed the ionic spiderweb to turn on the electrostatic adhesion only when a target was nearby in order to avoid undesirable contamination. The electrostatic vibration cleaning, which was reinforced by surface modifications, ensured the removal of inevitable contaminants, thus recovering the capturing capability of the ionic spiderwebs. Finally, an ionic spiderweb was fabricated in the form of an orb web. In initial state, the ionic spiderweb was contaminated with dust and thus could not capture any target. To eliminate the contaminants, a frequency of the applied voltage was swept from 30 to 60 Hz for 200 seconds, and the dust that covered the ionic spiderweb was significantly cleaned. After the cleaning, the ionic spiderweb was turned to sensing mode. When the ionic spiderweb sensed the approach of a target, it was rapidly converted to capturing mode. Various types of materials such as leaf, polymethyl methacrylate, glass, and aluminum were tightly captured by the electrostatic adhesion of the ionic spiderweb. After performing the mission, the targets were released by application of AC voltage to the ionic spiderweb. Our approach is potentially applicable to other existing robotic components based on electrostatics, such as electrostatic adhesion grippers, dielectric elastomer actuators, and capacitive tactile sensors. They are expected to equip additional functionalities and broaden the scope of applications, potentially without major structural changes. More importantly, the proposed ionic spiderwebs offers a design principle for soft robots that can achieve complementary interactions between each robotic component by emulating synergic functions of nature.